Hi dear children. Up to the previous class we were discussing about the chapter wave optics. We have seen about the wave picture as proposed by Christian Huygens. Then we have seen coherent and incoherent addition of waves. Then we have discussed about the famous Young's double slit experiment, which proved the existence of wave nature of light. Until now we were believing about the corpuscular theory, right? Then we have seen the single slit diffraction experiment, the conditions for formation of maxima and minima, its difference with the Young's double slit experiment, under what conditions diffraction will make way for interference, and then finally we have wounded up the chapter by concluding the Fresnel distance. So what my plan for today is starting the chapter number 11, and the 11th chapter is dual nature of radiation and matter. Dual nature. What do you mean by the term dual nature? Dual. There is two nature. Of what? Radiation. We have to see the dual nature of radiation. Then we have to see the dual nature of matter. So what is this dual nature is all about? Okay, already we said radiation has got wave nature. Then what else exists for radiation? So dual means there should be another nature also. And that is where we are coming to the idea of the particle nature of radiation. Wave nature, radiations possess both wave nature as well as particle nature. And in this class we are going to discuss about the particle nature of radiations. And that is where we will consider photoelectric effect in detail. Then we will look about the wave nature of matter. Obviously, matter has got particle nature. So first we will see the particle nature of radiation. Then we will see about the wave nature of matter, and that will be the topic of discussion for us today. In this chapter. So we are going to we are planning to discuss this chapter in 4 to 5 videos. Hope everything will be clear to you. So without wasting our time, let us first of all start this chapter by studying about what is called an electron volt. What do you mean by an electron volt? So 1 electron volt to be precise. So 1 electron volt may be defined as the energy required to accelerate an electron through a potential difference of 1 volt. It's the energy required to accelerate, or work done to accelerate. Work done to accelerate an electron through a potential difference of 1 volt. So we have studied about the formula for work done is equal to Q into delta V. So here Q is what? 1.6 into 10 to the power minus 19 coulomb. Then potential difference is 1 volt. So this is 1 volt. So this is 1.6 into 10 to the power minus 19 coulomb volt. Coulomb volt is nothing but joule. So this is equal to 1.6 into 10 to the power minus 19 joule. This is the value 1 electron volt. So 1 electron volt, this work done is equal to 1 electron volt. And let me tell you, the value of 1 electron volt is 1.6 into 10 to the power minus 19 joule. 1.6 into 10 to the power minus 19 joule is the value of 1 electron volt. From here I can say 1 joule is how much? 1 electron volt divided by 1.6 into 10 to the power minus 19. So this is equal to 6.25 multiplied by 10 raised to 18 electron volt. So this is the value of 1 joule. 1 joule is this much. 1 electron volt is this much. So remember these values. Now the question, why do we discuss about these values? First of all, let me tell you, electron volt is the smallest unit convenient for expressing the energy of subatomic particles like electrons, protons, neutrons, etc. Electrons, protons, neutrons, their energy can be conveniently expressed in the unit of what is called electron volt. That is the importance of the unit electron volt. So it is a convenient unit for expressing the energy of microscopic particles. Yes. An important concept to understand here. Now we will discuss about the next topic, that is regarding the methods of electron emission. So we know that electron, what is an electron? Electron is a microscopic particle, right? It's a microscopic particle, or it's a subatomic particle whose mass is 9.1 into 10 to the power minus 31 kilogram and charge is 1.6 into 10 to the power minus 19 coulomb, right? Electrons were first discovered by Sir J.J. Thomson, and its E by M ratio, specific charge ratio, was determined by Sir Millikan. All such things are familiar to us. So we will start this chapter basically by saying the topic what is called work function. So what do you mean by work function? Work function is defined as the minimum energy. It is the minimum energy required to remove electrons from the surface of a metal. The minimum energy required to remove remove electrons from the surface of a metal. The minimum amount of energy required to remove electrons from the surface of metal is called work function. And work function is expressed, so it is denoted by phi. Work function is denoted by phi. It's a symbol I am using. You can use different symbols, and its value is of the order of electron volt. The value of work function is of the order of electron volts, let me tell you. Sorry. Now, the value of work function is least for cesium. Least for cesium, which is about 2.14 electron volt. Which means what? Work function of cesium is 2.14 electron volt. That means we can remove an electron from a cesium atom if you give a minimum amount of energy is equal to this much. If you give an energy of 2.14 electron volt to cesium, it is possible to remove an electron from cesium. Right, so, and second point I would like to say is that the work function is greatest for platinum. I am saying PT, which is about 5.65 electron volt. So work function for platinum is 5.65 electron volt, whereas that for cesium is 2.14 electron volt. What does that mean? From which element it is possible for you to remove electrons easily? Which element can cause the removal of electrons pretty easily? Tell me, dear children. It is okay. Your answer is absolutely correct. It is for cesium, right? Electrons can be easily removed from cesium, but very difficult to remove electrons from platinum. And you can see from NCERT book table number 11.1 the order of electron volts. Sodium, generally alkali metals have low work function because they are ready to donate electron, right? If you want an electron, I am ready to give it, is what alkali elements are saying. Alkali elements are saying what? Yes, if you want electrons, please take from me, please take from me. So that means you have to give only less energy, right? Less energy is required to remove electrons from alkali metals. That's the reason why cesium, it's in group 1, right? It's a group 1 element, so one has to say its energy is very less. So, and again, one more thing we have to say, cesium is one of the outermost elements, elements in the higher order in group 1. So, it is far from the nucleus, so binding force will be less there. So, that's the reason why it has got low work function, I would say. Now, we will discuss about the methods of electron emission. Methods. What are the methods of emission of electrons from metals? Methods of emitting electrons. The first method I am saying is thermionic emission. Thermionic emission. Thermionic emission. What do you mean by thermionic? Thermionic. Answer is there itself. Thermionic. 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 What is thermionic? Simple. Electron emission by heating the metal. So it is the process of emission of electrons by heating the metal, right? Heat the metal, remove the electron. That is what is thermionic emission. So emission of electrons by heating the metal, that is called thermionic emission. Then second method of emission of electrons is called field emission. So what do you mean by field emission? So field emission means it's a method of emitting electrons by the application of the method of emission of electrons by the application of it's a method of emission of electrons by the application of strong electric field. So, method of emission by the application of a very strong electric field, very strong electric field, which is of the order of 10 raised to 8 volt per meter. So how much you have to apply is of the order of 10 raised to 8 volt per meter. That is the amount of. So that means, what is that meaning? So that means if you consider a region of length 1 meter, the potential difference need to be created is 10 raised to 8. What is 10 raised to 8 becomes 1 million means 10 raised to 6. 1 crore means 10 raised to 7. 10 crore, right? I'm not sure about the value. Just think about it. How much you have to give the potential difference for a length of 1 meter. Think about that potential difference. I think 1 lakh is 10 raised to 5, right? 1 million means 10 raised to 6. 1 crore means 10 raised to 7. 10 crore means 10 raised to 8. Great, right? It's a great value. So you need, for a length of 1 meter, the potential difference that you need to apply is about 10 raised to 8 volt. Great value. Huge value, huge potential you have to apply in order to remove electrons from the surface of metal. That is what we do with the field emission. Then the most important thing we have to see is regarding the third one, and that finds application in our chapter also, photoelectric emission. So what do you mean by photoelectric emission? Photo means light. Then what do you mean by photoelectric emission? So we can define photoelectric emission as the emission of electrons by the application of emission of electrons by the application of, or by, not application, I'm sorry, by light of suitable frequency, to be precise I have to say. Light of suitable frequency. The emission of electrons by whom? By whom? By kone. By light of suitable frequency, right? Emission of electrons by, come on children, light of suitable frequency, emission of electrons by light of suitable frequency. Who discovered it? Discovered by Sir Henry Church. When? Later it was studied in detail by Leonard and Horrocks, and together we call it as Leonard and Horrocks experiment. And this is a figure showing the experimental setup made by Leonard and Horrocks. So in their experiment, we have got a variable rheostat, that is resistance here. This is a variable resistance. So I'm sorry. So this is a variable resistance. We call it as rheostat. Now the resistance of the circuit can be varied accordingly. Okay, so now there is a voltmeter, and the purpose of this voltmeter is to measure the potential difference. As you can see here, the voltmeter is also connected between, this is called the cathode or the target plate, and this is anode, or otherwise we call as the collector plate. Now radiations of suitable frequency. So this is the place where radiations are incident. When radiations of suitable frequency is incident on this surface, electrons will be emitted and the electrons will be accelerated towards the collector plate or anode plate by the suitable applied potential difference. Now what is this all about? This part of the circuit is all about. What about this part of the circuit? Let me explain them. This is a three-way switch, a rotating switch I have to say. Now this point is the positive terminal of the battery. This point is the negative terminal of the battery, right? This is positive terminal of the battery. This point is negative terminal of the battery. So we can change the polarity of this cathode and anode plates by means of this rotating switches, I have to say, commutator switch, or otherwise we call by the name. Okay, so what I have to say is that at present, okay fine, this is connected to, so what I have to say is that when this connection is set up here, so let me consider the situation like this. Now here I'm making this connection active. A connection is set up here. Now it means this is positive, this is connected to the positive terminal of the battery, and when you insert this connection, this is connected to the negative terminal of the battery. Which means there exists an electric field inside this one in this direction. Electric field, because the direction of the electric field is from positive plate to the negative plate, and this is the direction of electric field here. Right. So in the experiment conducted by Leonard and Horrocks, their target plate or cathode, their cathode was zinc, and radiation used is ultraviolet radiations. The radiation that they have included in their experiment is ultraviolet radiation. So the target plate is zinc plate. So when zinc plate is irradiated with the ultraviolet radiation. Okay, so this is the basic experimental part I have to say first of all. Now we will consider the observations of this experiment. So with the condition that the electric field is still likewise. The first part of the observation we are going to discuss is regarding the variation of intensity versus photocurrent. Now we are here with a new word. What is that new word? Photocurrent. So far you have not heard about this word, what is called photocurrent. What do you mean by current? Current means flow. What do you mean by photocurrent? It is the electric current due to these photoelectrons. What do you mean by photoelectrons? These are electrons emitted or ejected through photoelectric effect. Electrons ejected through photoelectric effect is called photoelectrons. Electrons ejected through photoelectric effect is called photoelectrons. So we are going to study the variation of photocurrent with intensity. So I am going to take capital I for intensity and small I for photocurrent. Small I represents photocurrent, capital I represents intensity. If I plot a graph between the intensity of the incident radiation, or other photocurrent is on the y-axis, that is the dependent variable, and intensity of the incident light is dependent variable, and we consider for radiation of sufficient frequency or value which is greater than a certain one. The graph is observed is a straight line. The graph observed between the intensity of the incident radiation and photocurrent is a straight line. The graph is a straight line. Now what is the meaning of this graph? Look at this graph please and tell me what is the photocurrent when intensity equal to 0? What is the photocurrent when intensity of the incident radiation is 0? What is photocurrent when intensity of the incident radiation is 0? You can see here that the photocurrent is equal to 0, right? So I is equal to 0 when capital I is equal to 0. Which means that itself proves the photoelectric effect. Right? So, and then we can see that for a given photosensitive plate, photocurrent is directly proportional to intensity. Right? This graph shows that photocurrent, small I is directly proportional to capital I. What is small I? That is photoelectric current is directly proportional to the intensity of the incident radiation. That is observation number 1 made by Leonard and Horrocks. Coming on to the observation number 2. Observation number 2 made by Leonard and Horrocks. That is regarding the accelerating voltage. Second one is accelerating voltage versus photocurrent. This time the frequency of the incident radiation is kept constant. The frequency of the incident radiation is kept constant, whereas the experiment is repeated for different intensities. The experiment is repeated for different intensities. So frequency of the radiation is a constant and the experiment is repeated for different intensities. So voltage is on the x-axis, current is on the y-axis, and it is so this point corresponds to V is equal to 0. Now V is equal to 0 means what? It is not connected anywhere. The supply is not connected anywhere, that is what is V equal to 0. What do we expect about this graph? What should be our observation? When V is equal to 0, we are expecting photo current to be 0. But in reality, it is not equal to 0. In reality, it is not equal to 0. What does that mean? Even if the accelerating voltage is equal to 0, photoelectric current is not equal to 0, which means it has a finite value. And it is observed that the photo current is not equal to 0 and it increases, and then it attains a saturation value. Saturation means steady value. This is at intensity I1. Intensity I1. Now, okay, fine. So this is observed at one intensity. We have to think that what I'm saying, how wise they were in doing, how intelligent these people were concluding in their answers. That is why we call them a scientist. They are great people, and what they are doing, they are looking at every corner of the experiment study, right? They are taking into consideration every aspect. So this is what is observed at intensity I1. Now they study, yes, if this is the variation at one intensity say I1, what happens when intensity is changed? Okay, let's change the intensity. And this time it is observed that the graph is again likewise, but this is at intensity I2. Great. Okay, let us go with another intensity, one more intensity. And the graph is observed like this, I3. Yes, now I applied positive voltage, right? What is applied is positive voltage. Now what to do? Now let's do the next thing. So according to what we are going to do next is, okay, this connection is off there. There is a key close here. In the next observation, what is done is, instead of keeping likewise, okay, with your permission, instead of doing this, now they have connected likewise. This connection already exists. The connected likewise. What does that mean? Now that means, look at this terminal. This is positive, positive, positive. Comes here, comes here, comes here, comes here. Sorry. Yeah, fine. Positive terminal of the battery comes here, comes here, comes. Positive is connected here, right? Now this becomes positive, right? And that means now negative, yes. Now so let us open up here. So otherwise this is called a potential divider arrangement. Doesn't matter even if it exists or doesn't exist. This is potential difference. I'm just breaking it for the moment. Negative, right? What is the direction of this electric field? Yes, the direction of the electric field is likewise. As we all know, electrons always experience a force in the direction opposite to the electric field, right? Electrons always experience a force in the direction opposite to the electric field. That means what should happen? Will this electric field an accelerating electric field or decelerating electric field? Is this an accelerating or decelerating electric field? Accelerating or decelerating? Absolutely, it's a decelerating because electrons experience a force opposite to the electric field, right? This is the direction of the force on the electron, force on the electron. Now, electrons, when they try to run towards right, so electric field is pulling it backward. Electric field is pulling it backward, right? So electrons are trying to run forward, electric field is pulling it backward. What will happen to the electrons now? Will they start moving with greater speed or lesser speed? Will the electrons start moving with greater speed or smaller speed? What do you think? Obviously, when you are running and when you are pulled, you are running and you are pulled backwards by some forces, obviously you are not supposed to run fast, right? So speed of the electrons will decrease. When speed of the electrons decrease, the current due to them also must decrease, right? current with them also must decrease. So now I am applying a potential difference in the opposite sense. That is what it is done here. Earlier positive was connected to the positive terminal, negative was connected to the negative terminal. Now we have reversed the connection, right? As we reverse the connection, electrons will experience a decelerating force, and the purpose of this rheostat is to vary the supply voltage. Now I am varying the supply voltage. What happens? What happens? What happens? What happens? What happens? Electrons will slow down, 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 slow down. Finally comes to rest. This is what is observed at intensity I1. Then the second intensity I2. Again the observation that the electrons comes to rest at one particular point. Once they comes to rest, whatever be the voltage thereafter doesn't matter, the current remains to be zero only. And for the third case also they observe the same thing. Here you have the same frequency. I will tell you I1 less than I2 less than I3, right? So that means what? This potential difference, let us say this potential difference by name, say V0. At this particular potential, say V0, minus V0 I am saying because this is negative, right? At this potential difference, what is observed is that the photoelectric current is equal to 0. The photoelectric current is equal to 0 and the potential difference V0 is called stopping potential. The potential difference V0 is called stopping potential, otherwise called cut-off potential. This is called stopping potential or cut-off potential. How will we define this cut-off potential or stopping potential? The minimum value of the reverse voltage. So we can define stopping potential or cut-off potential as the minimum value of the reverse potential. Minimum value of the reverse potential which applied so that the photoelectric current just reduces to 0. I repeat, it is the minimum value, array, whose. It's a minimum value of whom. It's a minimum value of the reverse potential. Minimum value of the reverse potential at which the photoelectric current just reduces to 0. It is a minimum value of photoelectric current at which the it's a minimum value of the reverse potential. Minimum value of the reverse potential at which the photoelectric current just reduces to 0. At which the photoelectric current just reduces to 0. I repeat once more, it is a minimum value of the reverse potential at which the photoelectric current just reduces to 0. Just reduces to 0. That potential is called stopping potential or cut-off potential. So let's see now the third observation from them. Again the graph is same. Accelerating voltage versus photocurrent. This time they kept the intensity constant and the experiment is repeated for different frequencies. The experiment is repeated for different frequencies. Experiment is repeated for different frequencies. Okay, let's see the graph once more. Accelerating voltage on the x-axis and photocurrent is on the y-axis. Let's see the graph for different colors. Okay, so first they took, so all radiations have same intensity. So the photo saturation current is here. And this is V01. This is for light of frequency mu1. As I told you, the experiment is repeated for different frequencies. Now for a second frequency, the stopping potential is observed to be V02. For the second one, so what is observed same is the photo saturation current is observed to be same, and this at frequency nu2. I am saying nu2 greater than nu1. Nu2 greater than nu1, and what you could see here is that so in the previous graph what we have seen is that the photo saturation current is different for different frequencies, different intensities, but the value of the stopping potential is same for different intensities, right? I repeat, in the previous graph we have seen that the photo saturation current is different for different intensities, whereas the value of the stopping potential is same for all intensities. Now what is observation here? Photo saturation current is same. You can see that the photo saturation current, look carefully, photo saturation current is same for all frequencies. If you look at the first color, if you look at the second color, what is observation is that the photo saturation current is just the same. It is not going to change at all. Do you see any change here? Look, dear children, is there any change here? Do you find any change in the photo saturation current here? No change. Then what is here? The change comes in the stopping potential. The change comes in the stopping potential. So this is at frequency nu1, V01. This is at frequency nu2 and V02. What you see is that V02 greater than the value of V02 greater than the value of V01. Which means greater magnitude of potential is required. When frequency increases, greater value of stopping potential is required. Greater stopping potential is required because it's a value of the potential I meant. Right, so what you can see is that stopping potential increases as frequency increases. Stopping potential increases as frequency increases, right? What you see here is the value of the potential, the value of the reverse potential increases, the value of the potential increases with increase in frequency, right? So now we move to the next graph, that is the last graph here, last observation. So we have seen so far 3 observations. So now we will discuss about the variation of stopping potential with the frequency. Stopping potential with the frequency. So, nu. As the graph comes, there is, if you look at the graph, the shape of the graph is something like this. V0, nu0 I'm saying. So up to the frequency nu0, no photoelectric emission is possible. Up to the frequency nu0, no photoelectric emission is occurring. Thereafter, when the frequency is greater than nu0, the graph is a straight line. This is for metal 1. Now when the experiment was performed with another metal, okay, let me use another color. When the experiment was performed with another metal, it was observed that the graph is a straight line again. These two are parallel to each other. So nu02, nu01. So different metals, the variation of the stopping potential is different, but the graph are parallel, which means they have same slope. Same slope. Two lines are said to be parallel when they have same slope, right? They have same slope here. That means both have same inclination. Both have the same inclination, I have to say. So this is the idea regarding the experiment as conducted by Leonard and Horrocks after the discovery of photoelectric effect by Henry Schwartz in the year 1887. What are the conclusions we can arrive from here? Let us have the conclusions from this also. Conclusions regarding the photoelectric effect. So I can say the conclusions are what? Conclusions of photoelectric effect. Let us take the experiment. For a given photosensitive, so that frequency, I didn't say about the frequency nu zero. The frequency nu zero is called threshold frequency. It's called a threshold frequency. What do you mean by threshold frequency? The minimum frequency required to initiate photoelectric effect. Minimum frequency. Minimum frequency required to initiate photoelectric effect. So, the conclusions of the photoelectric effect we will see in the next video. Thank you.